Hello, my name is David Curran, and I'm here to talk to you today about how you can quickly build a question classification engine. So, I work as a machine learning engineer dealing with language, an area called natural language processing. Important thing to remember here is all the stuff I'm talking about today is based on checking the accuracy, checking how good you do, checking that when you claim a question is about this topic, is it? So everything here I might push over, but everything here is based on we check it, does it improve the accuracy? Let's move on. So that's the idea to keep in your head here, is that all of these sort of hand wavy arguments have to be backed up by something data at the end. So what is question classification? A question or a problem comes in from a user, and we have a known list of topics this could be about. And we want to come out and say, right, we know this question that says, how do I cancel my phone contract, is in the topic cancel contract, and we have a certain confidence. We want to say, right, this is what it is, this is what the question is asking about, and this is how accurate we are. This could be an email, but usually here we're talking about like instant messages on Facebook Messenger or WhatsApp or something like that. If in your head you keep the idea of spam versus real email, it's a good way to imagine, right, how would I look at the text in an email and decide whether it's a real email or it's a spam? And if you can get that into your head, if you can understand that, then trying to work out whether this is about a customer complaint or a customer compliment or a trying to upgrade, or it becomes, there's just more different buckets to be in. It's not that you get the basic concept. This area here is called supervised machine learning. And what does that mean? That means you're given examples of what you're trying to classify. So you have examples, what we call the ground truth, where utterances people have made, and these are labeled by a human labeler, or at least checked by a human labeler to say this is what they meant. So in an image classification problem, this would be pictures of cats and dogs. You have a picture of a cat, and the label will be cat. Or spam will be real email and spam email, and the spam will be labeled spam, and the real will be labeled real. So supervised machine learning, where we make up a data set and we use that to train up the system to say, right, this is kind of what you're looking for. And we have to make a system that's really good at saying, right, based on this training data, I'm really able to see what this classification should be. Now, there are systems like this built by Google and IBM, where they take in questions, example questions, and intent. And then when a new question comes in, they go, right, this is the intent I think it belongs to, and here's how sure I am, here's my confidence. There's other stuff they deal with, but we might talk about that a bit at the end. But the main thing here we're worried about is, if I get sent a question, how do I know what it means? That's the task here we're trying to make a program to do. So in terms of data, we had 3 data sets of 5 to 10,000 label utterances each, not 1,000 to 10,000. In Europe, what you tend to have to do is you sit on the shoulder of someone in the call center, or you get them to write down the questions people are asking. You get about 500 questions, maybe 1,000 that way. And over the course of developing a chatbot with user tests and everything else, you get up to about 2,000 questions. In China, the first day they hand over 10,000 questions to you. And then you have to go label that data and stuff, but the problem becomes too much data, not too little. So it's quite interesting that way. So data is the important thing. The data in this task is what someone has said and what label an expert would say they meant to say. Oh, that is get a new phone, or I had reception problems, some sort of topic they were talking about. Now, why would you build an AI engine? Why would you build a system that can take in this trained data, and then when a new question comes in, is able to tell you what they're talking about? You could just use one of the big guys' AI engines, but they won't deploy in China. I think it's something to do with sharing source code, but you'd have to use their server in Japan or whatever, and there's physics reasons why that just takes longer to get the answer back from. If you're a medium-sized company, you might want more control over the chatbot. You might want to just hand over your data to IBM and Google and all the rest of it. You might want to keep more control over it. That, particularly if you're in a particular niche, maybe those big companies are great at banks or insurance companies, but if you're a telecom or something like this, you understand telecom better than them. Maybe you can build an engine that's just better for telecom than they can. There is also problems with sending the data from China to Japan. Is that there's a connection? Sometimes the connection will break. The Great Firewall of China will get in the way. And there's a lot of data centers lying around that are new, particularly in China. And the idea of, oh look, we have an AI application deployed there, kind of makes them look a bit better. Look, we are eating our own dog food. We are using the data center to do this stuff. So in many ways, in terms of cost and everything, if they built a data center and you can build an AI engine in there, they'd love you to put it there. One thing to note is in the West, these sorts of IBM Watson engines are really, really cheap. They're effectively free. In China, they cost a lot of money. I don't quite know why, but cost, at least outside China, doesn't tend to be a reason. The big players in China do have these sort of AI engines, but they're really expensive. So now we get down to the nitty-gritty of what do you actually do to build an AI engine. So all these steps will be gone into more detail later, but just to roughly get the idea of the process that goes along, you need to read in the data. This is, I want to buy an iPhone, label iPhone buy. Read in the data. You want to separate that into words so that you know roughly here's what the text contains. That needs to be turned into a format that a machine can read. There are a few ways of doing this, but I'll go through the simplest one today. Then there's different manipulations you do on that data that the text can read. This data structure that a computer can understand and make classifications with. There's different manipulations you can do to boost the signal from the noise in that data structure. And then there's the actual classifier. So classifier could be something as simple as dot product of two vectors, or it could just be a word count, what's called a naive Bayes system. But the thing to remember here is what comes out of these tests, whether it's a k-fold test or a blind set test, is an accuracy score. We said this question was buy an iPhone. We look at it, we have it labeled as buy an iPhone. That was correct. Our accuracy there is 1 out of 1. And you usually have tests out of, with the k-fold test, a few thousand. With a blind set test, maybe it's only 1,000. But all of the manipulation you're doing, you're trying to improve that accuracy score. So you might start off with an engine that's 75% accurate, and as you improve the various different steps, you try to get it to 80. It's the sort of area you're talking in. So now talking about Chinese, and I do not speak Chinese, which is why this is slightly more difficult for me. Chinese text doesn't have spaces. Spaces were added to Latin by a bunch of Irish monks. So spaces aren't a normal thing in language. It seems kind of strange that spaces seems like an obvious thing to have, but Chinese text doesn't have it. And it allows them to make really good puns and jokes and stuff based on how you mix up words and everything. Next step, how you turn those words into something a machine can read, a computer can read. We use a thing called string to word vector. Then we go into some of the sort of other manipulations you do to improve your accuracy. And then there's always nuances in language because it's a human thing. There's always weirdness you haven't thought of, and you're trying to cover off as much of that as you can. So spelling, for example, is one of those. So a piece of text in Chinese won't have spaces in it. It'll look something like the first line here. And you need a program that will find where it thinks the spaces should go in and put them in. We tried loads of different systems. The best one we found was this LTPS. It's at ltp.ai. There are other ones. Again, try them. What you tend to do is do all the steps of a pipeline quite quickly, get a score rate, and you go back and start manipulating different parts of it to see if that accuracy testing score at the end is getting better. One thing that's really useful here is you're working with Chinese colleagues or someone who's a native speaker in that language, if you're doing this for Norwegian or Swedish or whatever, and they'll see mistakes that the segmenter is making. Well, Chinese is really the main one you need to segmenter in, that you wouldn't pick up just from an accuracy score. They'll see that something that in your domain is actually one word is seen as two words because the segmenter is not used to this. So maybe, for example, iPhone is seen as iPhone, and really that's one word, put them together. And you can sort of rapidly, with 10, maybe 20 rules fix a lot of the mistakes that a particular generic segmenter is making. But that's just one of those things where you get the best system you can, and then you use somebody who knows the language, and you've taught some of this stuff to help improve the quality then. So when we've gotten this text broken up into words using this library, next thing to do is turn those words into something that a machine can read. One way to do this is a vector. If you can imagine that you can turn a sentence into like an array of 0, 0, 1, 1, 0, 0, 1, then compare two different arrays. You can say, well, these two arrays are the same. Oh, look, if these two arrays are the same, we know they're asking the same question. Let's give back that label. So how this is done with string to word vector systems is you count up all the words that happen in all of your training data, and then, say alphabetically you have a vector, aardvark, airport, all the way up to zebra and those Z's there. And you say, right, make a vector of that. And then when a particular sentence comes in, a particular utterance comes in, we say, right, does it have the word aardvark? Does it have the word airport? Does it have all these words up to zebra? And that turns the utterance that comes in into a array of 0, 0, 1, 1, 0, 0, 0, 0. And then you can use those two different arrays as your comparison. There are other methods of doing this. There are more complicated things now with deep learning and stuff, but this is just a really simple out of the bag system that once you grasp, I turn all of the utterances that I've seen into an array, and then I can compare arrays. It makes the whole machine learning thing seem an awful lot less magical, if you know what I mean. So once you've got that array, there are other things you can do to boost the signal, to boost the noise, to reduce the noise and to boost the signal. So one of these things is TF-IDF. If you're reading an article about mobile phones and it mentions the iPhone 5 times, it's probably really about the iPhone. Do you know what I mean? And if it mentions it once, but Android 5 times, it's probably about Android. These sorts of things of how often a word is mentioned tells you more. That's fairly obvious. There's IDF as in how often you'd expect it to be mentioned, inverse document frequency, as in a really rare word tells you kind of more than a really common word. So iPhone, Android in telecom industry might be really common, but if someone starts talking about the iPhone 9 or some particular brand of iPhone, it tells you more because it's sort of a rarer thing. There's more surprise there. And then the stop words. Actually, I'll mention it. TF-IDF tends not to work in this task we're talking about particularly here of what is this utterance about, because there's only 13 or 14 words usually in most texts that people send in WhatsApp or in Facebook Messenger. So the chance of them using a word 3 or 4 times is pretty low. People just tend to, short sentences, and TF-IDF tends not to have that much. But again, it's part of your pipeline. You try it. If you increase the accuracy, you keep it. Usually it doesn't for this task. Stop words. The most common words in sort of European languages are sort of glue words to stick sentences together. If you remove them, it sort of, again, increases the signal, reduces the noise. It can help slightly increase the accuracy. This isn't the case in Chinese. So, we tried them, didn't increase the accuracy, remove those common stop words. We don't have that as our pipeline. Next idea here is n-grams, which is like how big a window are you looking at of words? Do you look at each word individually, or do you look at I want to cancel my phone contract? Is phone and contract individually just in the array at random locations? All the information looks extract from it, or is the fact that they're together, you put that in as the useful information? It's how big a window do you want to look at, because you can't look at the entire sentence. If you think of just looking at one word at a time and just comparing the individual words in an utterance, you get most of the idea. Now, there are other issues with Chinese. The way spelling mistakes happen is totally different to in English. It's things that sound the same become spelling mistakes. A lot of the time with these sort of systems, you end up taking an off-the-shelf spelling corrector because they just work a lot better. It's one of those things, one of the early machine learning triumphs was spelling correction. So Sometimes you just take an off-the-shelf spelling corrector with a few different tweaks to find things that aren't spelling mistakes in your domain. So, the name of your company, the name of your brand, these sort of things might be seen as not real words, but you just add them into the spelling corrector and say, no, they are allowed. That is a proper word here. The Chinese based in a system called Pinyin that was invented by a guy who died in like 2018. Be pretty impressive to have on your LinkedIn, like I invented text. But anyway, it's an amazing system, and they can type really, really fast with it and stuff. In something I hadn't mentioned is stemming. In English, if you think of words like, say, consider, considered, consideration, all of these kind of mean the same thing, and you can sort of stand them down to say, if they use one of these consider words, just treat it as consider. That doesn't actually work in Chinese. The stemming just doesn't work the same way, so there's no point having it. But in English, it's one of the processing steps you usually at least check, and usually it helps. In Taiwan, they still use the traditional non-pinyin version of text. It's a bit hard to devise apparently, but it's kind of like a regex you can use to transliterate from one to the other. So it's not something you really need to worry about. It's a mechanical process to turn pinyin into traditional Chinese text and vice versa. But with any language, and particularly with Chinese, there's a huge amount of other stuff going on. And what we're just trying to do here is build an accurate classifier quickly, and then we can go back and worry about the other stuff later. So a simple pipeline that works quite well, as in pretty much as accurate as, about 2% off Watson accuracy, is use the LTP segmenter to find the words in Chinese, turn that into a word vec. Here, because we did decent size of data set, it was worth it occurred 3 times. We only kept 1,000 words, which is quite low. In general, though, you don't tend to keep much more than 2,000 words, at least for these sort of utterance tasks. And bigrams, we looked at 2 words at a time. You check unigram, bigram, trigram, etc. I've never seen much more than 3 words at a time being useful. Maybe with massive data sets it is, but in this case, 2 words at a time gave you a bit more information. And then there's a particular classifier called a support vector machine that's really quick to build models of. And this particular version of it was the one with the highest accuracy. The reason why that's useful is if you go through all those steps we talked about, and then you have a classifier that takes a day to train, then it takes you a day to find out whether you want to keep words that have occurred twice or 3 times, or words that have only occurred once or 4 times, or whatever it is, and your improvement iterative cycle is much slower. So a really quick, good classifier like SVMs are in this process can get you a lot of the rest of the things decided quickly. And then maybe if you want to go to a fancy dancy other longer model classifier later, you've still got an awful lot of the intuition built up of what should work and what shouldn't. So support vector machines, if you're interested, you can find out about these yourself, but basically it's trying to define a good way to separate out 2 different classes of things. So cancel my phone contract, renew my phone contract. Let's try and make some sort of like rules that will divide the 2 and separate them out really well. And they work really fast now, which is great. Now here are some hacks, and this kind of gets into the dark arts of NLP. One of the major ones is entities are sort of unique things that happen in utterances. So I want to buy a plane ticket. Buy a plane ticket. That's it. You can see that that's the intent. Buy a ticket. I want to buy a plane ticket from London to Dublin. All right, that's really useful. If you're going to make the API call that actually buys that ticket, you're going to need to know where and when and these sorts of information, these sort of entities that are unique. But where they can be useful in classifications is if you feed back in, oh wait, it isn't just Dublin, they've said, it isn't just London, it's 2 cities. What sort of intent mention cities? Well, buying a plane ticket, that ups the chances that what they're talking about is buying a plane ticket. They're probably not going to mention cities when they're talking about picking a meal. Well, they might, but it just reduces the chances. So one thing you can do is you can sort of augment the training data and also the data when it comes in, that when you see an entity, that's part of the vector, that's part of the thing you're comparing. And that has a pretty good improvement on accuracy. It's just a simple, well, relatively simple thing you can do to improve accuracy. Sometimes what you want to do is a thing called part of speech tagging, where the verbs, the nouns, the proper nouns, these sort of the parts of the text are labeled, and that can be used, fed back into the classification algorithm to improve the accuracy. I've not found it's worth the hassle usually. It's one of those ones you go, well, it's improved things a bit, but I'm not sure it's worth the complication we've added to the system. We'll come back and look at it later, and you never quite get back to look at it. There are other things, there's papers around Chinese and using that part of speech tagging, a thing called the root of the parse tree to improve accuracy. Again, we tried it didn't work enough that it was worth the hassle. We'll come back to it. There's always for these things, do you want it now or do you want a pretty trade-off? And a lot of the time you have a comparison with the Googles, the IBMs, and you can get really close to them or even slightly better. Great, and we'll come back and make it even better again later. Is actually the system now, in this system, the build a quick system, get it out the door, there wasn't deep learning. You can pretty easily now, it's gone an awful lot easier recently to use sort of deep learning methods. SpaCy in particular is very easy to use if you're talking about word embeddings. Sorry, what are word embeddings? We kind of know how related words are, but if you've only ever seen like a vector, 1,000 words, you don't have that relationship. You don't know that suitcase and luggage are kind of similar, or that baggage and luggage are kind of similar. You're just relying upon people having used all these words somewhere in the intent, in the training data. But in the case where someone comes along with a new word you've not seen before, that's going to fail. So word embeddings allow that if you've not seen luggage, but you've seen suitcase and baggage before, when someone asks a new question that's similar to the other questions, but with this new word, you can say, oh, wait, no, I think that's kind of similar. I kind of know what luggage means, even though it's not in my explicit training data set. So they're really useful that way, and they've gotten an awful lot easier to work with now. So it's something that's easy enough to add to your system. But you're moving away from the strict string to word vector system, then the easy one to deal with. So a basic proof of concept, using this pipeline. I'm not a web programmer, but I could build like a Flask API that when you call this with a piece of JSON that said classify this text, it could send you back an answer that on a laptop worked in 0.2 of a second, and you could build that in a day. Like this sort of stuff with Flask is really easy to sort of combine a text classifying pipeline with just some sort of simple API that can get called. Now, of course, there's security and scaling and all this other stuff that has to happen. But just to show your boss, look, we can build a classifier here in this unusual language that happens to be important for my business that would classify, people's emails or what it is quite well. You can show this to the boss in a few days. Something I mentioned earlier was that this, entities and dialogue flows. Dialogue flows is when there's a back and forward, to walk someone through the steps that they need to do something complicated like book a flight or, buy a new phone or something like this. And there's a open source system called RASA that's quite good at handling these entities and dialogue flows. There's a fairly steep learning curve because just the format of how they structure the data. It's really easy to put this into a Docker image and then, just deploy it like that. The engine I've been describing today is it's a part of that pipeline in RASA. It's really easy just to plug into that pipeline. They have a pipeline for Chinese, for Chinese language classification, but it's not nearly as good as the one I described. It's much, much less accurate. I think it's like 10 or 15% less accurate. It was really not very good at all. But, you can just simply put in your Python code here into this and it'll work, quite easily. So that's the other parts we haven't talked about here, the entities, the dialogue, even the analytics. RASA can cover for you. It's maybe not as quite as shiny and nice as the IBMs or the dialogue flow version, the UI, but it'll work, and certainly an engineer or anyone like this can handle this sort of stuff. Okay, so usually I give talks on how to clean up data and stuff. There's another talk coming either soon or maybe you've already seen it, about how to manipulate your data and get your data really good. But the other section of natural language processing is how to make a classification engine. And this was just a quick talk today to describe a very simple classification engine that has accuracy up there with the big guys that you can build in a few days. Thank you very much.